Today I will talk about science and policy aspects of climate change, and of course there is incredibly much to tell about it. To bring a little bit of a focus into this, so I will bring you some general context and then kind of go more into the aspects of land use and land use change, agriculture and air pollution, and even there, not everything, because nobody can talk about everything. But I thought it would be useful to explain why I talk about science and policy. The reason is obvious. That's my job currently at the Joint Research Center. And to give you a general idea of what the JRC, which is part of the European Commission, is supposed to do, is very much about science and knowledge to support EU policies with independent evidence throughout the whole policy cycle. And what does that mean, the whole policy cycle? It means from the anticipation to the execution, to the ex-post analysis, basically analyzing did the policy work, did it deliver. And as you can imagine, there is quite some science involved in that as well. So JRC has a very big settlement here in Italy, in Ispra, but there are also different JRCs in different locations. The Batten Institute in the Netherlands is focusing on energy systems. The Gale settlement in Belgium is doing reference materials. Council is doing nuclear materials. Seville is doing economic analysis, and then by far the biggest settlement is in Ispra, where we look at the whole range of different things, from environmental climate change to disaster risk management to border security, you name it, it's there. Just to give you an impression, this is Ispra, the Lago Maggiore, and you can imagine, of course, it's a nice place to work. It's a beautiful place. We don't see the mountains as often, as clear as here. There's a lot of pollution, of course, but every 10 days per year, I think you have such a beautiful view on the mountains. Okay, let's move to climate change. I'm sure you all have heard about the Paris Agreement. It's actually not only the Paris Agreement, but the Paris Agreement followed the acceptance of the Sustainable Development Agenda for 2030 in 2015, and then December 2015 was the Paris Agreement. And basically, the Paris Agreement is about setting the targets, well below 2 degrees, limiting climate change to well below 2 degrees as kind of the framework. But how to get there and what that all means has a lot of consequences. So, in contrast to the earlier Kyoto Protocol, Paris has not only things about mitigation, but also adaptation is there. And there is a separate climate fund that is sponsoring adaptation, development of adaptation strategies in developing countries. And this was actually the secret, this was kind of the enabler why almost all parties endorsed the Paris Agreement. Without this, it wouldn't have worked. So where is science entering? Well, of course, if you do mitigation and adaptation, and if there's money involved, you want to know, is it working? Are we going into the right direction? Now, for mitigation, there is already some kind of a framework to measure progress. It's called MRV, Measuring, Reporting and Verifying Framework. These are the steps that are involved. It includes monitoring. But for adaptation, such a framework is not really there. And obviously, to really understand, are adaptation measures actually protecting as they should be protecting? Is the money wisely spent? There's a lot of science that has to flow into this as well as of course the technology development. Okay. Important to mention that the Paris Agreement foresees a framework of monitoring the whole process, which also requires science inputs. That's just to give you some words on what is the science behind the Paris Agreement and generally the framework program on climate change, UNFCCC. This is a slide that is showing the development of the so-called Intergovernmental Panel on Climate Change, or Ipcc. Was started in 1988, and then there was this sequence of reports, the first assessment report. Then in 2013 we had the fifth assessment report, or AR5. And all these reports are kind of linked to some policy events. They provided input and the impetus to start doing certain things, like the Kyoto Protocol, including adaptation, settling the foundation under the 2-degree limit, etc. We're now here. Special reports on reaching 1.5 degree made a lot of press. It was basically about showing or analyzing what would be needed to reach a temperature increase of only 1.5 degree. That's incredibly ambitious, obviously, but also showing what would be the benefits of this. It's a very interesting report, and if you're interested in this field, I would really recommend to at least read the summary for policymakers. You should be able to read that. But if you're interested in more, there are interesting chapters there after. There are 2 other special reports at the moment in the making. The special report on land, which I'm going to talk a little bit about later. It's not published yet, but it's now in the stage of being approved by the policymakers. And there is the special report on oceans and cryosphere, and then a little special report on developing further the methodologies to measure emissions, basically, because you have to agree on how you measure that. Very technical work. Most people will never see that, but if you're into this, it's of course a must to read it. The big effort is now coming in the AR6 sequence of reports. I'm also participating in one of these working groups, and that is scheduled to be released in the time frame of 2021-22. This AR6 sequence of reports is then meant to inform the next global stocktake, and what that is I try to explain you now. So basically, the Paris Agreement is working like this. Countries will have to outline their national determined contributions. That is basically the plans, what they want to do on mitigation and adaptation. And the global stocktake basically means if you take all the national plans together, all the parties' plans together, are we on the right way to reach the overall goals, the world goal of limiting climate change to less than 2 degrees. Ipcc 6th assessment report is going to kind of give all the evidence, including observation-based measurement, observation-based evidence, modeling, all the things that are needed to kind of evaluate if we're on the right track. Then there is a new NDC that is kind of adapting to the needs, and that goes then into a cycle ahead and hopefully leading to better results. Okay, so probably you have also seen this. This is global mean temperature increase from 1850 to now, basically, taken in this case from the WMO State of the Climate report. Just a few headlines. You see here these different lines. These are different products. You see that things were maybe different between these projects when data were not so present, and then it starts kind of depending on interpretations of what was happening. But that's not really longer the case when you grow up all these products. We're pretty sure if you have a global temperature increase, we can measure it. And some headlines of this report: 2018, 4th warmest year on record globally. We had of course in 2018 also this major drought event in Northern Europe, quite good conditions in Southern Europe, so it's all kind of locally different. But then also 2015, 2018 were the four warmest years on record, and warming is continuing. These are the messages from WMO. Regarding oceans, I think this is quite important, because if we are warming the climate system, where does all the heat go? It goes for 90% into the oceans. And until maybe 20, 30 years ago, we couldn't really measure that very well. But there has been a new observation system. We can measure pretty well how much sea temperature until depth is increasing. And you can calculate how much heat went into this. So ocean heat content, which is a measure of climate change, is also at record high. And global mean sea level continues to rise quite fastly. Headlines are things like sea ice extent that remain below the average of 30 years in the past. So this is all nice, global temperatures and the consequences. Of course, we know that on land temperatures are generally increasing faster, and connected to temperatures, but also quite importantly the whole hydrology. There are a lot of impacts that are happening and that will happen. So this is a graph from another document issued by the European Commission, outlining its vision, where we want to be and what we want to avoid by 2050. Also highly readable, kind of seeing where in Europe the field is moving to. Anyhow, in that report there is this graph here showing all the different impacts across Europe. They're quite different going from the north to the south. I cannot read obviously all these impacts here, but what you can see is that one of the regions that is going to be more impacted is the Mediterranean. But all these different things like increases in heat extremes, increasing droughts, loss of agricultural productivity, to things like spillover effects, say immigration, that is also climate driven. So we need to understand basically what are the impacts and what are the adaptation potentials to do something about it. So one of the works JRC-wide we're doing is the so-called CETA studies, which is about an economic integration of biophysical and economic impacts across different impacts. And here you see 5 of them. So it's integrated assessment, if you would like. So you need a lot of different people to work together. Not easy at all. I think you know how difficult it is also here in Torino. But it's quite an achievement, and so one of the things that we have been doing in my group is estimating the agricultural impacts, and here the story is basically that the disadvantages and the benefits will be quite differently distributed over Europe. We might even expect some benefits in Northern Europe and stronger negative effects in the south related to this whole story of temperatures and water, basically. So another message that you can take up from this is a scenario that looks at climate change of 2 degrees by the end of the century, but avoiding 2 degrees will still not avoid all the impacts and damages. And adaptation will be there. And you all have seen what is happening. It's the way we're going now. We will of course not completely reach the 2 degrees targets unless we're going to speed up things. Okay, so an example again from my group. This is crop yields of, in this case, rain-fed wheat. It's a bit difficult to see the colors, but believe me, here it's a bit greenish positive. Here it's a bit reddish negative. What you can also see is that some of the countries have are really the solid colors, and the other ones are striped. So what does this mean? Well, in climate sciences you need sufficient time periods to demonstrate a change. Just looking at a couple of years doesn't tell you it was climate change. And typically we use periods of 30 years to compare, which is maybe still not enough, but you might get rid of some of the natural variability. Well, these striped lines basically tell you, yes, it's negative, but it's still not statistically significant. Meaning, and the most important consequence of this is basically that variability of production is going to increase a lot, and that's a problem. I mean, it's good, of course, if in one year you have a nice production. It's not good at all, especially for farmers, but for food security in general, if the other year is record low. So that is variability increasing. That is one of the biggest issue. And of course, this is a simulation where we do not include adaptation options. You can sometimes do something about it, but it's also important to understand the limitations of what you can do. Yeah? Okay, let's move on. Another example from my group, global, this case, maize. It's the major crop worldwide. Yearly production about 1 billion tons. And what we do here is using a combined heat and water stress index and correlating it with observed meteorological variability, intraannual variability. So what can you see here? This is global maize production. This is kind of a central estimate of a climate model, and this is the observed one. So you see from one year to the other, you can have maybe a 10% variation of maize production worldwide, observed, reported to FAO. And the climate model over this period is roughly capturing this variability. Now, the analysis uses then climate scenarios into the future, say from 2020 onwards, and one of the kind of surprising findings is that already in the next decade, the worse variability that we have seen in the past will become the norm in the next decade. So things are going to change. Then if you go ahead, so here we have reached more or less 1.5 degree temperature change. Here we're at 2 degrees. By 2040, we are already going to losses of 15 to 20% and onwards. So, increase in frequency and intensities of extremes could lead to substantial production declines and increasing variability, which challenges our options for adaptation. Okay, so we are actually importing also quite some maize from elsewhere. So if globally things are going to change, we are going to feel that also in Europe, and it's also having a consequence for Europe itself. All right, so I'm switching gear now to observations. It's kind of a bit reverse of what most people would do in a climate presentation. Here is some of the evidence from the paleo records on greenhouse gas concentrations for the last 800,000 years, or the last 2,000 years, and then when we have more accurate information. So for the last 800,000 years, that's basically how far the ice cores can bring us. Well, people are trying to bring that back to 2 million years perhaps. You see all these glaciation and interglacial events which are showing up in CO2 and in the other two important greenhouse gases, methane and N2O. And then coming to more or less the current era, and here we have the current climate, the current period where concentrations are really skyrocketing. This is the same plot, but then amplified. You see already a little bit better what kind of observations are behind it. Here, from Arctic and Antarctic drills. And amplifying this picture here, you basically see how much now the concentrations are increasing. Here we still, until 1950, about we have to rely on ice cores, and then we started observing first CO2 at Mauna Loa, and now there is a whole global network, and even satellites are able to measure things like CO2 and methane. Okay, so observations are getting better, and from these observations we can also learn on where the emissions are, how strong they are, etc. Okay, some of the key messages. There are actually ways of extending this via proxy records back 100 million years. And we know that it's about 60 million years ago that CO2 was as high as it is reaching now. So that is actually, you know, if you think about it, that's amazing. It has been higher further back in time. And actually, maybe 120 million years ago, concentrations were as high as we expect in a worst case scenario by 2100. So, you know, in 100 years we're doing what otherwise would have taken 50 million years. Also for N2O and methane, at least 800,000 years hasn't been as high, but we don't have any evidence for what was happening before. So, but I think what I was already telling, the rate of change is perhaps the most important thing. We're changing things at least 10 to 100 times as fast, concentrations, as has been happening at any time in the past. Okay, so difficult to read the red thing. This is from the 1.5 degree report. So we want to do something about it. We want to stop the increase of concentrations and the effect on the atmosphere. And what can you do about it? So the basic schematic and thinking is that by the middle of the century, emissions, the balance of emissions and removals have to lead to carbon neutrality. So net emissions are going to be zero here, basically 2050. And it's obvious that that energy system and fossil fuel use has to be substantially reduced, and that things like deforestation, CO2 emissions have to go down and be turned into rather a sink of carbon. But it's of course also quite clear that if you don't manage to follow this trajectory, but for instance this one here, and you still want to reach this neutrality, the role for the sinks, for this carbon uptake, for instance in vegetation or with bioenergy, carbon capture and storage, will have to be larger. So there's this whole field of tension and this idea, if you don't reach it here, you have to do it somewhere else. The overall effect is what counts. Okay? And this is obviously another scenario where you reduce fossil much faster, and then your dependence on other technologies has to be less. Okay, so some words on the carbon cycle. So where does it come from? Where does it go to currently? Fossil fuels at the moment, 87% of the CO2 emissions, and deforestation in the tropics, mostly the other 12%. That goes for 46% in the atmosphere, that is kind of these increasing curves. And then the other half, more or less, goes equally into the oceans and into terrestrial ecosystems. And that is basically one of the important themes at the moment, that this terrestrial ecosystems, they are part of the problem, and they might also be part of the solution. And in policy terms, we call this LULUCF, land use change and forestry. That is a fixed meaning in Ipcc, UN, FCCC context. But there are issues there related to science. So this is a bit preluding to the Ipcc land report. If you look at what countries are reporting in terms of sinks for LULUCF, they're quite a bit more optimistic than what science-based assessments are telling. And that doesn't necessarily mean that countries are cheating, but it might be more related to how things are being defined. What is the human factor? What is the natural factor? How do you account for that? But in the end, of course, we need to understand the overall carbon balance, because that's what you see in the atmosphere. So we estimate, and that's actually work which was based on work done at the JRC, we estimate that there is currently about a 10% of the overall emissions mismatch between inventories and science-based methods, and it's something we quite urgently have to solve. Okay. Just to explain a little bit better, if we talk about land and land emissions, we're in the mitigation part of the talk here. Anything related to livestock, to artificial fertilizer, manure, etc., that is called agriculture. And anything related to uptake of carbon in the biosphere, including agriculture, is called LULUCF. Yeah? So that's how the Ipcc, UNFCCC, but also the European policies are putting things apart. So they're both important, and they both have their specific challenges. So important is that agriculture is mostly human-induced, where LULUCF has this factor of natural variability that you need to understand and discount for in an objective and honest way, without cheating, basically. Okay? So, I don't expect you to read everything here, but we have in Europe a policy that the countries are implementing, basically the member states. The policy for 2030 is to reach in the emissions trading scheme, a 43% reduction, so that goes a long way towards this 2050 objective of making that almost zero, or maybe 80% reduction. But emissions trading is not all sectors. It's the power, energy sector, industry, aviation. And then you have this other part, which is all the other emissions, which can be either under effort sharing. Here the overall objective of all these sectors together would be 30%. And our objectives for LULUCF. And basically, the whole framework is built like this, that it recognizes that countries have different specific conditions to reach objectives, and if you do more here, you can discount somewhere else to a certain amount. There is this flexibility that if you do more here, you may have to do less here. So countries can choose, and that's again was an important aspect to reach agreement of countries, because they think, well, we can do more on the forest, or we have a good control on the industrial emissions, and such things all play a role in making that happen. So here, good to mention that science is still there. For instance, here we had a big risk that there was too much flexibility in having the baseline conditions, and that would basically lead to nothing happening properly. So we were quite essential to establish baseline levels and sound scientific methods. Okay, I mentioned this communication before. This is Europe's view on how emissions should develop. Here you see quite a bit more detail. You see here the power sector, industry, transport, etc., etc. And here is the role of LULUCF. In Europe, land use is already a sink for carbon. We don't have a lot of deforestation. Instead, we have afforestation. And here is this carbon removal technologies coming in. So again, overall objective to get towards zero net emissions by 2015, which doesn't mean that all emissions will be zero. I think it's very hard to imagine that, but it means that whatever you don't reach here, you have to compensate somewhere else. And you can quite obviously imagine different scenarios. But important to mention here is that all the cards are at the moment into reducing fossil emissions, but what we will be stuck with is agricultural emissions, where things will probably be quite a bit harder to reduce. So there is this also this notion of agriculture part of the problem and maybe also part of the solution. What could be one of these solutions? It's a big topic, carbon uptake in agricultural soils. It's also one of the key objectives in the forthcoming Common Agricultural Policy, which has to be much more climate relevant, both in terms of mitigation and adaptation. And we're doing specific work at JRC. My colleague Emanuele Dugato provided me with this slide. So we're doing a lot of monitoring, regular soil sampling across Europe, monitoring how much carbon is changing. Well, you can imagine it's changing slowly, per definition. That's how it works. So you have to kind of keep doing it over a longer time to really have experimental evidence of things changing. But the nice thing Emanuele has been doing is also kind of having a bit more integrated modeling of different adaptation options. So this is, for instance, the option that you keep your crop residues on the soil and don't till the soil as much as you would do in conventional farming, which is indeed over time leading to good results, and positively also it doesn't have too much side effects in terms of N2O emissions. On the other hand, putting and fixing crops like clover will initially give good results in fixing carbon, but then you start increasing also your nitrogen amount in the soils, and you get it out at some point as greenhouse gas emissions, as nitrate leaching to groundwater. So over 40, 50 year timescales, this might actually have a detrimental effect on the greenhouse gas balance. So, with other words, if you do things, you need to know what you're doing and assess it in a quite holistic way. Okay, agricultural emissions in Europe is about 10%, where you can see that this upper red and blue part are related to animals, and the lower part here is mostly related to soils. So this is to a large extent methane, and this is N2O. And I think the issue there is that in general, compared to reducing fossil emissions, reducing emissions in agriculture is still quite expensive, not for everything. For methane, there might be some good possibilities. But still, having in mind this 2050 objective, where agriculture remains as one of these last things, it's becoming more and more clear that we don't only have to look at agriculture, but at the food system as a whole. It's about human diets, about reaching health benefits, and kind of making a bit of a societal change to change our attitudes towards eating meat and improve the situation. Okay, I'm coming to the last part of my presentation, a little bit more focused on work that I've been doing myself on methane and air quality. So, methane, I believe there is some work here at Polytechnico also on methane, but it's the second most important greenhouse gas on a 100-year time scale, probably a bit more important on shorter time scales, but it's also a precursor gas that can produce tropospheric ozone, which is an air pollutant. Okay, it's playing a role. Obviously, it stays in the atmosphere about 10 years, so it has kind of a hemisphere to global scale effect. Worth to mention that current thinking is that 55 to 65% of the emissions are anthropogenic, and we're talking about 330 teragram, and altogether methane emissions of 550, 600 teragrams. These methane concentrations are behaving a bit strange in the atmosphere. So what basically happened was that it was increasing, then we had a period that it was stabilizing, everybody happy of course, and now it's skyrocketing again. And the question is, what is it? Where is it coming from? And if we know where it's coming from, can we do something about it? The question we try to address here, however, is a slightly different one. How would it help reducing ozone air pollutants? Yeah? So would it help if we would reduce even stronger methane emissions in Europe and control European air pollution, or do we really need to have regional to global cooperation? Okay, what is happening with ozone in Europe? The key message from the EMAP assessment, from the LERTAP assessment report, is that ozone peak concentrations are declining, but the average values are not. And something is compensating there. And the question is what is the role of methane there? Okay, some words on what do we know about emission trends. Here I use our JRC EDCAR database, which has a lot of the greenhouse gases included. Basically what you can see, what we know from activity data of several sectors, is that methane, if any, has been increasing in the last decade or so, related to a number of things: agriculture, wastewater and solid waste, and fuel production and transformation. If you produce oil and gas, you lose methane and away. Okay, picture for Europe is quite different. Here we see a decline due to several reasons. For instance, we have seen the implementation of the landfill direction. We're collecting our humido, our waste, which is all helping to reduce methane. But also the closure of many of the coal mines in Europe has been quite an important factor in reducing methane emissions. These mines need to be ventilated. That typically went directly into the atmosphere. Was quite important source. Interesting also for agriculture. You can see here around 1990 the introduction of the milk quota. So suddenly farmers were allowed to have much less cows, but it was in a way also an incentive to do more with less. So if you're a little bit aware of it, cows are now producing much more milk per animal than they used in the past. And as a consequence, they also per animal produce less methane. And these are all kind of factors that are playing a role in understanding what is determining such curves. Okay, it's not everywhere the same in the world. Here, this is the methane budget for the EU. You see agriculture is here 44% and waste still 30%, and fuel exploitation in Europe 20%. But the fuel factor in North America and Russia in the Middle East is much larger. Well, for instance, in South America, agriculture, and in Australia, agriculture is much more important. Overall, if you look at the sheer numbers, it's kind of clear that countries like China are becoming the major source of methane worldwide. So they're already at 20% or so. Okay, coming back to what that means for ozone. So we use all this data, we put it into models, and try to estimate what did it mean. So these are model simulations simulating ozone Europe average, so it's just an indicator, I would say, locally different. You see ozone has been increasing by 6-7 ppb up till here, and then kind of going over the top and declining again. So, or more or less flat if you want. This is the contribution of the classical air pollutants, kind of peaking earlier and then declining. This is the contribution of ozone, which has been produced somewhere else, US, Asia, wherever, is slowly starting to decline, and that is mainly because of similar things happening in North America than what has been happening in Europe. But then the methane contribution has not peaked yet. This is an analysis from the Task Force Hemispheric Transport Air Pollution. If we look at what that could mean for the future, here are 3 different scenarios. Very briefly, this is current legislation. This is a climate policy focusing on the energy sector, not really on agriculture. And this is something that is considering all the technological options that we have currently available, that are available if you would implement them towards 2030, 2050. So the basic thing is, if we go on, we might still reduce a little bit ozone, and then it starts increasing again. That's quite consistent with the picture that I showed before. Climate scenarios might help a little bit, but implementing all these technologies might help a lot more and bring us back to levels that we haven't seen maybe in the 1960s, 1970s. These are, if you try to attribute that, these are the local effects. What can you do locally? What is the effect of things happening remotely? So all the upwind regions. And you see also here, if you would be able to implement things in India or China and make the air cleaner, it will have a benefit also for us in the long run, because the atmosphere is transporting things. And here is the contribution of methane, and here you see really this divergence. If we do nothing, we might increase by 2 ppb annual average, or decrease by 1 to 2 ppb. And that is kind of a wedge of 3 ppb, okay? That's kind of summarizing the whole story. So what we did recently at JRC was taking many more scenarios that are being made in the climate context, and see a little bit what is now the scope of climate reductions to help also the ozone problem, because that might be an extra argument to do something about it. You know? So we take scenarios from the new Ipcc framework, from the old framework, the ones that I showed before, some internal JRC scenarios that are informing our EU policies. And basically you see here kind of this clusters of scenarios appearing. Those that are high are basically non-sustainable, everything goes on as expected. We use more fossil fuels, we produce more agricultural products, etc. Then there is kind of the stabilization scenarios and the progressive scenarios that are really declining emissions. So what you can see is basically mitigation potentials across different sectors in the order of 150 to 250 teragrams by 2030 and 300 to 450 by 2050. So that's the difference between something that we really don't want to happen and something which is very positive and working on all the aspects that you can imagine. So several things for the climate to say about this. So that would be 2.1 to 3.4 gigaton CO2 equivalent, 10% of the current emissions, quite important. In other terms, it could help closing 12 to 20% of the current 2 degrees emission gap. So if you would focus on this, you can much quicker get to your temperature targets. So that is climate. But it's also useful, coming back to the theme, to see what that means for ozone. And here you have each time this kind of most negative scenario, most positive scenario for these 4 scenario families across the world. So one thing that you can see already is that ozone will not respond equally across the world. You have here the global, but for instance the Middle East is very sensitive to ozone pollution, and that the reason for this is that it's very conductive to produce ozone, the atmosphere. But overall the picture emerges that there is this big wedge of doing something that will avoid a negative situation in the order of 6 to 8 ppb. Okay. You can also calculate what that means in terms of avoided mortalities due to air pollution. What is being done there is you use model calculations of how ozone will develop, and you convolute that with functions that are based on statistical analysis of how ozone pollution is related to premature mortality, done, for instance, by the Global Burden of Disease Project or the WHO. So what you find then for this whole cluster of scenarios, that depending on the scenarios, by 2050 you might have worldwide 100,000 more deaths globally due to air pollution, which is large. It's not as large as, for instance, the pollution by particulate matter, which is in the order of 5 million, but it's still quite substantial. Or you might avoid in the order of 32 to 40,000 deaths related to methane reductions, basically. So it's an analysis of how it would help. How much would this be in Europe? In the order of 10,000 deaths, which is in the same order of magnitude as the amount of deaths due to traffic in Europe. So it gives you a little bit of a perspective of if this is important or not. A key conclusion of this report was that the benefits are quite globally distributed, not completely equally, but still quite globally. So global mitigation strategies are more effective in reaching such goals. Okay. Challenges. I think politically, we all know what is happening worldwide, and it's really important that we keep this momentum of the Paris Agreement. What we try to achieve is to have robust scientific methods that are being applied worldwide, everywhere, in a transparent way, and basically make sure that also developing countries have access to data and knowledge to drive this political change and to keep them aboard, basically. I think politically it's also a huge challenge, of course, to get the societal change that will be needed to transform the energy system, the food system, etc., etc. And that's why we need reachable goals. You saw the example of the European Union setting a 2030 goal, having already set out the ambitions, what we want to achieve by 2050. UNFCCC, Ipcc, they're doing more or less the same thing. So sketching the road, where do we want to be, and making all kind of local initiatives fitting into this story. I don't think it's there is always a lot of talk about how much this will cost and this and that. But in fact, if you put this in economic models, there's also a lot of opportunities. If you start investing in new technologies, all these things, it will be a huge boost for economy as well. So I think that's something, that's a mindset change that we still have to achieve in a way. Okay, for the science, there are a lot of things that I didn't discuss here, but I think there's this kind of increasing understanding of what are safe boundaries. Maybe 2 degrees or 1.5 degrees is a safe boundary globally, but there are more of these boundaries. But for all these things, to understand what does it mean, what is safe, we need integrated analysis, Earth system analysis, modeling, analysis of risks, tipping points is still quite scary to me. I mean, there are a lot of things we don't know, and what is the risk that you reach a threshold and go the wrong way. Observations, you're doing quite some of that here. I think Earth observations are now really taking off and have a lot of capacity and potential, and there are enormous amounts of new things happening at the moment, so a lot of opportunities to do interesting things. I talked about this mitigation story again. It all will, this is the big picture, but it has to be local actions to do it, enabled by the correct policy framework. I was talking a little bit about co-benefits. There are a lot of other reasons why we should be doing mitigate climate emissions. Air pollution was one of them. I talked about the kind of the LULUCF agricultural issues. There is the competition for land that you need to think about. You can grow all the biocrops that you want. If the land is finite, you might not be able to do that, or do something wrong somewhere else. This coupling to sustainable development goals. Climate is somehow everywhere. It will rely on a lot of these sustainable development goals and progress on things, but it's also contributing to things like safe water and reducing poverty and all these things. For adaptation, at JRC we're really not very strong at understanding adaptation. There is also a reason for this. In the European policy, adaptation is the domain of the member states, but there is an overall objective at EU level that wants to push this forward. So one of the things that are issues is reducing the costs of adaptation options, but also just things like barriers. Farmers are not always very keen on, late in their career, still changing things, so they keep doing what they have been doing. And here, generational change might actually offer opportunities. Also, improving climate predictions is something important. At the moment, we run our climate models, but we don't really have a real forecast capacity beyond 2-3 months ahead. Then it becomes like random. If we could improve this towards a couple of years, you can imagine, if you know what will be more or less the weather and the weather extremes in the coming years, you can much more effectively do your planning for a lot of different things. For adaptation as well, integrated analysis, make sure that what you do here is not wrong for somewhere else. I think water is an important example. If you use the water here and somewhere else you don't have the water anymore, it's going to be a problem. And that is not only within Italy, but it's across Europe, because many of the rivers cross many countries. Okay, but maybe the ultimate challenge, and this is a slide that some colleagues from Ipcc have been showing, take some time to read it. It's about keep telling the message, and sometimes having the feeling that people are willing to listen to anybody in terms of democracy of science. But I think we have a lot to tell in Ipcc, and I would recommend you here as scientists to read these things and communicate it as well. That's it. Thank you for listening.